Hello, welcome to this video. So in this video we're going to be talking about black holes. We're not going to be worrying about general relativity. So for those of you who do not like tensors or Christoffel symbols or any of the strange jargon of general relativity, don't worry. We'll be using just Newtonian physics because the idea of black holes as something called dark stars actually emerged shortly after Newton published his law of gravity. So yeah, we can talk a lot about them without even worrying really about general relativity. At some point I'm hoping to make a general relativity playlist where we'll talk about black holes from the perspective of general relativity too. But anyway, this video is going to be about black holes, it's going to be about event horizons, and to understand the physics and the geometry, particularly of black holes, we have to understand something called the escape velocity. So for the first half of the video, we'll talk about the escape velocity, firstly generally, then from the Earth, and then we'll build up to talking about black holes. So if we're going to talk about black holes, we need to talk about a concept called escape velocity. Because a black hole is all about the idea that if light falls inside of it, and we're going to discuss exactly what inside of it means, then the light can't escape, so the light can't get out. And that's to do with the speed of light and the escape velocity of the surface of the black hole, which divides the exterior from the black hole to the interior of the black hole. So if we're thinking about something escaping, we need to consider gravity and how gravity resists something escaping. And usually if you throw something up into the air, you're going to give it some initial kinetic energy. But as that object travels upwards, it's doing work against the gravitational field, and so the gravity is going to try to pull it down. And we describe this action of gravity by saying that the object that's been thrown up, your test particle if you like, is gaining gravitational potential energy. So the object loses kinetic energy because it does work against gravity, but to conserve the total energy, it must gain some kind of potential energy, and we'll call that potential in this case the gravitational potential energy. And usually when you throw something up, and probably all the times you've thrown something up, it will eventually come back down. And that's because given the amount of kinetic energy you provide to the test particle, it will only be able to travel a finite distance before all of that kinetic energy has been converted into gravitational potential. And when that object reaches its maximum height, it's lost all of its kinetic energy and it only has gravitational potential energy. Therefore, in that instant, in that moment in time, it's essentially static. And therefore, its future movement is just described by a downward force acting on an initially stationary object, if we're calling that initial point, the point where that object is momentarily still when it's reached its maximum height. However, whilst gravity slows things down, gravity does get weaker the further upwards an object travels. Now, usually that decrease in the gravitational field strength is minuscule, given the height objects tend to reach. However, gravity does diminish, and because of that, it is possible to provide a finite amount of energy that will actually allow the object to travel all the way to infinity. And it's essentially a kind of natural inevitable conclusion of the idea that the more kinetic energy you provide something, the higher upwards it will be able to travel before it falls back down, combined with the idea that the strength of gravity actually diminishes as the object goes further up. And when you give something just enough kinetic energy initially to escape the gravitational field of a planet completely, that is to travel all the way to infinity with no added forces acting on the object apart from gravity, then we say that you've given the object speed, an initial speed, which is equal to the escape velocity. So the escape velocity corresponds to the velocity an object has if it has just enough kinetic energy to completely escape the gravitational pull of another object by just going to infinity before it runs out of kinetic energy. You could, of course, provide something with more kinetic energy than the minimum kinetic energy required for it to be able to escape the gravitational field, but all that would happen then is the object would, travel a fixed distance in less time. But the point is, there is a finite energy and therefore finite velocity at which, if something initially has this, it will be able to travel all the way to infinity and will never come back down. So now we're going to look at calculating the gravitational potential energy. And we'll do this because you're probably very familiar with the kinetic energy. However, the gravitational potential energy, which we need to, work out, the changing the gravitational potential energy as an object travels, and therefore by how much its kinetic energy diminishes from one point to another. The equation for gravitational potential may be a little less familiar. The other reason is at GCSE, the equation for gravitational potential energy actually assumes that the strength of gravity is constant as an object moves, and that's because an object isn't moving very far from the surface of a planet, so we can treat to a good approximation the strength of gravity to be nearly a constant. And therefore the gravitational field strength is often quoted as some constant number. However, if an object is moving from the surface of a planet all the way to an infinite distance from that planet, then clearly the gravitational the gravitational field strength is going to change over that journey. It's going to be very strong when the object is on the surface of the planet, but it's going to be effectively zero when the object is at an infinite distance from the planet. So if we're going to calculate the work done, we need to take into account the changing gravitational force, and we do that by having a generic equation for the gravitational force on an object. And this equation is Newton's law of gravity. G, capital G here is a constant. We use capital G because smaller case G is usually used for gravitational field strength, which, as I mentioned, is not a constant for our purposes. Capital M is the mass of the planet, or later on it'll be the mass of the black hole, which is generating the gravitational force. Well, it's the principal generator of gravitational force we're worried about. Lowercase m is the mass of the test particle, so the object that is moving. So in the image we have, it would be the mass of the tennis ball. And r is the distance between our test particle, so the object that is moving, and the centre of gravity of the planet or black hole. And this equation makes kind of sense, because, clearly as r increases, the strength of gravity is going to diminish, which is what we would expect. Also, heavier planets, so planets with larger values of capital M will generate a stronger gravitational force, which is also what we would expect. Also, the gravitational force on a test particle or the tennis ball, for example, is proportional to the mass of the tennis ball, which is what we expect. Weight is proportional to mass. It's why in everyday language we confuse the terms weight and mass. And so, Newton's law of gravity makes kind of sense for what we know about the gravitational force. Now it's worth saying, this isn't going to be really important for this video, but for future videos it might be. It's worth saying that this equation, works as long as we can consider the planet to be, well, we can approximate it to be, a point particle, and we can also approximate our test particle to be a point particle. Where this equation, well, you can use this equation to build up forces of gravity where you're considering extended particles, but you do have to do some maths wizardry. So for example, if we're talking about the gravitational force inside of a planet, then, because our test particle would be inside the planet, you can't consider the planet to be a point particle because the planet has to have some finite volume for the test particle to be within it. In which case you do have to do some maths wizardry. You can't just say the force of gravity on the test particle is gm over r squared. You have to, split the Earth into lots of, the planet into point particles and then use Newton's law accordingly. As I say, that's not important for this video, but it is worth mentioning. Because, we'll probably at some point on this channel worry about the gravitational force of a particle if it's within the object generating the gravitational force. But anyway, for our purposes, our test particle is always outside of the object. And as our particle is moving to infinity, it's doing work against the gravitational force. And to get the work, if the force is constant, you can just do the work done is equal to force times the distance the test particle has moved. So in our case, F times r. However, as we say, the force of gravity is diminishing for our case, because we're considering an object moving a very long distance, all the way to infinity. So F is, clearly changing, and so you can get the total work done by breaking the journey into infinitesimal segments with the distance dr and going, well, over that infinitesimal segment the gravitational force is a constant because that segment is infinitesimal, so the object doesn't really make any progress away from the planet over that infinitesimal segment, in which case the work done over that infinitesimal segment is just F times dr. But then to get the total work done, we have to sum over all those infinitesimal segments, and that's essentially what the integral is. It's a sum over, an infinitesimal number, an infinite number of infinitesimal segments or things. Now, the equation we have, or end up with for the potential energy, which is minus gmm over r, has a minus sign in, and you might wonder, why is the potential energy negative? Well, it's essentially to ensure that the total energy is conserved. So, essentially, it's easier really to think about the minus sign if we're considering the particle starting at infinity and drifting towards, a planet. Well, as an object moves towards a planet, it's going to accelerate and it's going to move faster. The gravitational force will be, increasing its kinetic energy, because the object is essentially falling. But if the kinetic energy increases, then to conserve the total energy, the potential energy must decrease. And that ensures that the total energy will be constant for a test particle. Because there's always an exchange of kinetic to potential, so if you increase kinetic, you have to decrease potential. So the potential energy will drop as R increases. Sorry, as R decreases, because our object is moving towards the planet. But at infinity, the potential energy should be zero, because the gravitational force is zero. So in other words, as an object moves closer to a planet, so as R decreases, then the potential energy has to diminish from zero. So, the potential energy has to essentially become more and more negative, and that's why we have a negative sign. If we didn't have a negative sign, then we would essentially be saying that, as an object falls towards a planet, both its kinetic energy and potential energy increase, which would violate the conservation of energy. So we have to have that minus sign there. It's essentially going, if kinetic energy goes up, potential energy goes down, and vice versa. If the kinetic energy goes down, the potential energy will go up, but will reach zero at an infinite distance. And here are all the values for the symbols that go into Newton's law, and also the absolute gravitational potential energy, which has the minus sign here. It's worth saying, for our purposes, we're not really worried about the minus sign because we're interested in a change in gravitational potential energy, and because the gravitational potential energy, it's never going to be positive, the minus sign doesn't really matter for our purposes. It is important though for consistency with physics and ensuring things like the conservation of energy still works. And as I mentioned, you could ask, why is the gravitational potential energy negative? And I put in here an explanation in words because it's a question that can often confuse people. I know when I was doing A-level, I found it somewhat disturbing having negative energy, and it's really only at uni where I properly understood what the minus sign meant, so it's worth writing it here explicitly. But now we have an equation for the gravitational potential energy, we can, work out, well, how much gravitational potential energy would an object gain if it's going from the surface of a planet to infinity, or the surface of a black hole to infinity. And, if we set that equal to the initial kinetic energy we give to the object, then we'll get an equation ultimately for the escape velocity, because we'll find the velocity something we need to travel at to have just enough initial kinetic energy to travel to infinity by converting all that kinetic energy into gravitational potential. So we've had at the moment a look at the idea of the absolute gravitational potential energy, and now we try to keep the equation general. We gave the gravitational potential energy for an object at any arbitrary distance from the centre of mass of the other object that is generating the gravitational pull. However, if we're considering escape velocity, we tend to be considering something trying to escape from the surface of the planet or object, meaning the kind of gravitational potential energy we're interested in is really the gravitational potential energy for something at the surface of, a spherical body. And therefore, we're going to be using, a very particular gravitational potential energy, and this gravitational potential energy, the gravitational potential energy for something at the surface of a planet, will be lost when something fired from the surface tries to move away from that object generating the gravity. And, we have the escape velocity to be the velocity at which the object has just enough kinetic energy for it to lose all its gravitational potential energy and go all the way to infinity. So, the GP lost is going to equal the gravitational potential on the surface of the planet or object, which is Gm over capital R, where R is the radius of the object. Now Gm over capital R is the change in GPE, because that's equal to the GPE at infinity, which is 0 minus the GPE on the surface of the object. And because the GPE for finite values of small r is negative, when we do 0 minus the GPE, we end up with a positive answer, which is plus GMM over capital R. And then we can rearrange this equation, and we have an equation now for the escape velocity. So essentially, if something is fired off the surface of a planet, or later on to be a black hole, at the escape velocity, it can travel all the way to infinity away from that object. And the idea of escape velocity is crucial, because we define a black hole to be, an object which has, if you like, some hypothetical surface, even if it's just a region in space for which the escape velocity is the speed of light. So the equation for escape velocity is very important to us. Now we have a general equation for it. We can try to find the escape velocity for an object we are fairly familiar with, the Earth. Now the Earth is almost perfectly spherical. It's not quite, but it's to a very, very good approximation of a sphere, so we can use our equation for the escape velocity. And if we look at the mass and the radius of the Earth, and these are things you can get from looking at kind of the gravitational pull of the Earth by measuring the acceleration as an object falls. You can get to these values in lots of different ways. But using these values, and the fact that G, the universal gravitational field strength, is 6.67 times 10 to the minus 11, we get that the escape velocity from the surface of the Earth is about 11 kilometers per second. Now this explains why you have not probably ever jumped and managed to travel off to infinity. It's because the velocity at which we tend to fire things off the Earth is very, very significantly below this escape velocity. The only time when we're really considering things moving potentially faster than this escape velocity within the vicinity of the Earth is really if we're looking at things like molecules of gas, because for particularly light molecules, at kind of room temperature, they have so much energy that their velocity can, in certain cases, exceed the escape velocity. And this explains why our atmosphere doesn't contain much helium. Our planet's gravity isn't strong enough to hold on to helium, because the escape velocity of the Earth is 11 kilometers per second approximately, whereas the kinetic energy of a helium molecule at about room temperature exceeds this drastically. Well, not necessarily drastically, but it does exceed the escape velocity. And, if you're interested, you can work that out using the ideal gas equation from physics, or the equation of state. And and I'll probably do a video on it at some point. But this equation is useful not just for firing things off the surface of the Earth or defining black holes, but also for looking at what gases a planet of a particular radius and mass can and cannot hold on to. And so it tells us something about whether a planet might be able to, harbour life or not. So it's pretty cool, really, in that respect. Now I've talked a little bit about, black holes very vaguely. Let's move on to the really meat of this video and talk about them in more detail. Now it's worth saying I'm going to be looking at black holes classically, so using Newton's law of gravity. I will not be using Einstein's theory of general relativity. However, if we look at the size of a black hole, it turns out, at least for non-rotating black holes, both the classical Newtonian theory and the relativistic theory actually agree. Now, black holes are something that has mystified and still continues to mystify scientists. I mean, there's lots of debate as to whether black holes even, exist. There are some hypotheses that said black holes might actually be frozen stars, so objects that have collapsed just below their event horizon, but thanks to some kind of, quantum-generated pressure, actually resist any further collapse. And this would prevent black holes having any singularities. It would also resolve certain issues to do with entropy and the way that at least Newtonian black holes seem to destroy entropy. There's a lot of ideas around black holes, and particularly the interior of them. But if we're looking at the exterior, we're on pretty firm footing for arguing how they behave and how they interact with other things in the universe. And what do we mean by outside or inside a black hole? Well, the gap is defined by some kind of surface. And this surface can exist if matter kind of, collapses to a particular point, because, looking at our equation for the escape velocity before, clearly as the mass of an object increases and its radius decreases, or if you kept the mass constant but decreased its radius, the escape velocity from that object would increase. And since the speed of light is finite, there must be some finite value for the radius or mass, well, really the ratio between the radius and mass, for which the escape velocity is equal to or even exceeds the speed of light. So clearly we can have objects which have the right mass to radius ratio for them to be able to have a surface, at least in principle, where that surface has an escape velocity equal to the speed of light. And you might ask, well, does that surface in space or that region in space still exist if an object collapses even beyond that point? So say we have, for example, a really heavy, like 8 solar mass star. It's, undergone the supernova, but the core remains and the core collapses. At some point, the core might become, might have the right mass to radius ratio for the escape velocity from that core to equal the speed of light. But if that core keeps collapsing and its radius gets smaller, does this surface where the escape velocity equals the speed of light, or this region in space, still exist? Because the object has now collapsed past, well, beyond that point, it's shrunk below it. So does this surface still exist? Can we meaningfully talk about it? Because there's now no longer any matter there. But here we can use a nice property of gravity in Newtonian physics. And this property essentially says, providing you're outside of an object, and that object is spherical and has uniform density, then the gravitational force you would feel from that object is actually independent of the radius of the object, meaning even if our core of our star collapses below the region where the escape velocity is the speed of light, our object will still generate a surface somewhere in space, or a region in space where the escape velocity is equal to the speed of light. So, that way we can go, if an object keeps collapsing, it will inevitably end up resulting in producing a region in space where the escape velocity is the speed of light, even if there's no matter actually within this spherical shell of space, if you like. We call this region where the escape velocity is the speed of light, we call this region the event horizon of a black hole. And a black hole is essentially it's a region in space, and it's a region in space which contains matter which has contracted so much that around that matter is kind of a region in space which has an escape velocity equal to the speed of light. And we call this region in space the event horizon of a black hole. That's what I was saying, there isn't usually anything actually on the event horizon of a black hole. Well, actually, that's a bit ambiguous. Because of time dilation, you as an external observer would consider an astronaut falling into a black hole to be stuck essentially at the event horizon forever, or very, very, very close to it. But if you were falling into a black hole, unless that black hole was active, like black hole in active galactic nuclei, then you would be unlikely to encounter anything near you as you crossed the event horizon of a black hole. So really the surface of a black hole is defined by the gravitational pull at that region in space. It's not defined by any matter actually present on the event horizon. And that's why talking about the surface or size of a black hole has to be taken with a grain of salt. Because we're really talking about a region in space and relating that to escape velocity or the gravitational field. We're not actually saying that if you were plunged into a black hole you would find matter that is making up the black hole around the event horizon. So let's have a go at calculating a formula that gives us the size of a black hole. Now remember, when we say size, we're really meaning finding the radius from the matter concentrated at the heart of the black hole, for which the escape velocity from this region in space is equal to the speed of light. So if we were finding the size of a black hole's event horizon, we'd have to use our equation for the escape velocity. And remember, an object will thankfully only form a black hole if its radius is below the radius of the event horizon it would form, if it was to make a black hole. So most objects' radius far exceed the radius of their corresponding event horizon if they were going to make a black hole, and therefore most objects are not black holes. But anyway, let's go on with getting an equation for the size of the event horizon. So here we have a good old equation that relates the escape velocity from a spherical object to the mass of that object and the radius of that object. And if we set the escape velocity to equal the speed of light, then, well, the radius is by definition the radius of the event horizon, or, it gives us the size of the event horizon of the black hole. In other words, the radius of this spherical shell in space, if you like, for which the escape velocity is equal to the speed of light. and doing a bit of rearranging, we have this. Now, it's worth saying that the equation here for the event horizon of a black hole explains why objects don't form black holes in our universe very readily, but it also implies that in potentially other universes with possibly different fundamental constants, black holes might be, maybe one of the most common macroscopic objects, in those universes. Because we can see that the radius of the event horizon depends not only on the mass of the black hole, but on two constants. One, the kind of universal gravitational constant, capital G, and that tells us about the strength of gravity. And then we have another constant, the speed of light. But both these things are, as far as we know, there's no deep reason why G or C should have particular values. For our particular universe, G is very small, gravity is very weak, and C, the speed of light, is very large compared to everyday velocities, and correspondingly, the size of an event horizon is tiny, meaning most objects far exceed the radius of the event horizon they would have if they were going to collapse into a black hole. Meaning most objects are not black holes in our universe. However, you could consider a universe where G might be a lot bigger, so corresponding to much stronger gravity, and the speed of light might be really, really small in such universes. Also, it might just be that that's the case, in which case you could have a very large value for the size of an event horizon, meaning most objects would possibly in that universe be smaller than the event horizon, and therefore would class as a black hole. So it's worth thinking that we're kind of quite lucky in terms of human survival to live in a universe where black holes are rare, but that requires a small value for G, so weak gravity, and also the speed of light to be incredibly fast. There are some disadvantages to having a very high speed of light, particularly if we want to develop into a galactic civilization. The kind of speed of light being so, well, in some ways it would be problematic. The speed of light being, so huge, mainly in the sense that we wouldn't be able to readily make use of relativistic effects without giving objects tons and tons of energy to get them close to this very large speed of light. And making use of relativistic effects, particularly length contraction, would be hugely useful for travelling very long distances. But anyway, in our universe, black holes are fairly rare. They can exist, and they do exist, which is good, particularly for the formation of large galaxies. But black holes are rare. And for a bit of fun, let's try to calculate the size of an event horizon of something we're much more familiar with than black holes. Let's consider the Earth. So our question is, if the Earth was going to turn into a black hole, what would its event horizon be? What size would it have for its event horizon? And therefore also, what radius must the Earth shrink below in order for the Earth to form a black hole? Is an equivalent way of putting the question. Well, for the event horizon of the Earth, we need the mass of the Earth. And, using the mass of the Earth we have when we looked at escape velocity from the Earth, we find that actually the radius of the event horizon the Earth would form if it was going to collapse into a black hole would be 5.8 millimetres, so about half a centimetre. And obviously, it's not, there's no really realistic process as far as we are aware where the Earth would spontaneously or by some interaction suddenly, diminish in radius to below, half a centimetre, so the Earth is, not really going to become a black hole, and we don't need to worry about that. So, that's, that's why the Earth is a black hole, and we've also discussed why black holes are somewhat rare in our universe. But now we have a radius for kind of black holes, we can do a little bit more before we finish up. So now we've talked a little bit about the radius of black holes and their size, we're in a position where we can talk about the density of a black hole. Now I wanted to talk about density because the density of a black hole is actually really surprising. So black holes you might think would increase in density as their mass increases. However, it turns out that this is not necessarily the case, and as a glimpse of why this might be, if we think back to the equation for the size of the event horizon of a black hole, we can see it increases as the mass of a black hole increases. And so, as a black hole gains more mass, yes, its mass increases, but also its radius or its volume will increase. Meaning that there's, a question mark around, well, given this increase in volume, would the density still increase? Would the density remain the same, or would the density actually drop? And so that's what we're going to be looking at and trying to answer in this part of the video. So for this, we start with an equation that defines the density of a black hole, or really the density of anything, because black holes are exotic objects, but they don't change our core definition for density. So density is the amount of mass which is contained within 1 unit of volume. So usually we measure density in kilograms per metre cubed, but whatever units you use, density is about how concentrated the mass is in space, so mass per unit volume. If we're going to calculate the density of a black hole, we therefore need to know something about its volume, and we can get the volume from the radius of the black hole, or the radius of the event horizon. So here we have our equation for the radius of the event horizon of a black hole. And bearing in mind that black holes are spherical, or well, at least the event horizon of a black hole is spherical. In fact, it's perfectly spherical, according to standard Newtonian physics, because gravity is so strong at this point, there are no imperfections to this perfect sphere. So we have the volume of a sphere here, and given that black holes are spherical, and we have the radius of the black hole, or the radius of the event horizon, we can now find an equation for the volume of a black hole in terms of the mass of the black hole. And this gives us our equation here. So for a black hole, the volume is proportional to mass cubed. So essentially the volume of a black hole would increase quite drastically as the mass increases. And if we want to get the density, we have to do mass over volume. And when you do mass over volume, you end up with this equation. But we can write it a little neater by collecting all the constants into a single term. And we have this bottom equation for the density of a black hole. And we can see that, as the mass of the black hole increases, the density drops. At least, for smallish values of mass, the density drops quite sharply. as the mass increases, the diminishing, dropping, the amount density drops by diminishes also. And an interesting thing is, there's no real lower limit on the density of a black hole because there's no upper limit on the mass of a black hole. Say maybe the mass of the whole universe, but since we don't know the mass of the universe, at least if there is a upper limit on mass, that upper limit is pretty huge. So, black holes can actually have incredibly low density. Now, for stellar mass black holes, so, black holes which have formed when the kind of core that's left over after a supernova of a massive star begins to collapse, the density is pretty huge. But for really heavy black holes, really massive black holes, like those at the centre of, galaxies, their densities are actually, pretty small, at least compared to stellar mass black holes. And I was kind of curious, like, in our universe, what's kind of like the black hole with the smallest density? Well, that would be the black hole that we know of with the largest mass. And as far as I could find, the black hole with the largest mass is called TON 618, I think an appropriate name, at least of the TON bit. And when you put in, the mass of this black hole, which we can get by looking at how stars orbit around this black hole, particularly, the radius of the orbits and the, corresponding time periods, you end up getting that the density of this, huge black hole is about 4.3 grams per meter cubed. That's not kilograms per meter cubed, that's grams per meter cubed, and that's actually much less dense than the air you breathe. So, black holes can have really, really small densities, which I think is pretty cool. So anyway, that's everything on this video in terms of density of black holes, and really we can wrap up the discussion of black holes here. But to finish with, I'd like to say a little bit about what I'm doing on Patreon, for those of you who might be interested in hearing what kind of other content related to core physics is happening even outside of this channel. Hello, so I'm just going to be talking about what will be coming up next on this channel. So we've looked in this video at Newtonian black holes, but we missed out one feature that can play into them both classically and in terms of their general relativistic behaviour. And that's that as a star collapses to form a black hole, that star is generally rotating. I mean, our sun, for example, is rotating. I think it takes around 24 days to do one complete rotation, something like that. And as the object collapses to conserve angular momentum, it actually spins faster and faster. So black holes should be spinning at a really quick rate. And an effect of this is it introduces a centrifugal force which actually diminishes the size of the event horizon and can lead to the possibility of naked singularities. So we'll look at that in an oncoming video. I'm also going to be working on finishing the special relativity playlist, looking at the quantum mechanics of particles, which from our perspective travel back in time, so particles called tachyons. We'll talk about neutrino oscillation and how that comes about due to neutrinos having incredibly tiny masses, and then we'll also talk about paradoxes in relativity, both paradoxes which are well understood and also ones that require a bit of philosophy to explore further, like the one called the twin paradox, where the maths is generally agreed upon, but how to physically interpret the maths and where the true solution of this paradox lies is still very much debated. And there's actually something that has brought about a whole array of philosophies in relativity. So we'll probably finish the series by talking about the philosophy of relativity and how paradoxes can give insights into how to interpret the mathematics. And I'm also hoping to kind of start a Patreon kind of channel at some point. When I do, I'll make a video available on YouTube, just kind of announcing it and saying what the tiers are. But I'm hoping to make a Patreon channel where I'll share more, if you like, personal content. I mean, when I say personal, I mean things like my own experiences learning physics, experiences I've heard from other people, the kind of physics and maths books I'm reading, where I get the inspiration from to make particular videos, and just give a bit more kind of insight into kind of my experience of the world of physics, and have a more kind of personal channel on Patreon. But anyway, there'll be details of that if and when it comes along. But I'm really hoping to set up a Patreon channel as well. But anyway, that's everything for this video. So I hope you've learned something about black holes, and I'm hoping to see you on the video about rotating black holes too, hopefully soon.